Yeah, so my research broadly focuses on current tensions and anomalies in cosmology. So my work sits somewhere at the interface of statistical methods and cosmological data analysis. So I approach this from a few different angles. One is testing beyond lambda CDM models against current data sets, like the first half of my talk that I'll be presenting today. Another approach is forecasting what future surveys might tell us regarding these beyond lambda CDM models and studying how different cosmological parameters interplay with each other. So today, of course, I want to talk about a specific class of such models, which are interacting dark sectors, and what current data and upcoming surveys can tell us about them. This is based on three papers, two published in MNRAS and the third on Archive from earlier this year. Now, I know dark sector interactions kind of tend to split the room. Like there are people who find them exciting and others who think they're completely unphysical. And that is perfectly fine. I'm not here to convince everyone or to take sides. What I want to do is something simpler. I want to explain why people even consider these models and what do the latest observations say about them and what we find when we test them under a unified framework, so to say. So please feel free to interrupt me. I would rather have a good conversation than just deliver a monologue. Okay, so I'm sure this is very, very fundamental for the audience here, but still, one of the most remarkable things about modern cosmology is that we can describe the universe extremely well using just six parameters, the lambda CDM model. It fits the cosmic microwave background, large scale structure, and supernovae observations remarkably well. For most purposes, it works beautifully. But when we start comparing high precision data sets, small cracks begin to appear, which we know as cosmological tensions, which are not small discrepancies anymore. We are talking about several sigma discrepancies. So the Hubble tension is the better known of these, and as you all know, early universe measurements from Planck give H naught around 67 or so, 67.4, while local distance ladder measurements from shoes, for example, give you around 73, and they have very tight error bars. So the depending on what sort of data set combination you consider, this tension can vary from 5 to even 7 sigma. And this issue is robust enough that explanation through experimental systematics is kind of becoming not possible as days go by. Uh, Related to this, there is also something called the clustering tension in the S8 or the sigmoid parameter, which quantifies the amplitude of matter fluctuations in large scale structure. So CMB predicts slightly more clustering than what late time weak lensing surveys observe. So historically, this was a less severe tension, around 3 sigma or so, and some recent papers have suggested that it may be even less severe than thought. So I won't overstate it. Nevertheless, alleviating the clustering tension without worsening the Hubble tension has been a non-trivial challenge that partly motivated our work to begin with. So given the persistence of these tensions, we could either question the data for systematics, as I already mentioned, or if the data is not at fault, there is strong motivation to explore extensions to lambda CDM. Now, I mean, there are many classes of models in the literature. There's early dark energy, modified gravity, interacting dark sectors, and so on and so forth. There's a thorough review. I mean, there are multiple reviews in the literature on this, which I'm sure many of you are aware of. Of course, I'll not go into the details of each of them. The broad point that I want to convey is that most models tend to address one tension at the expense of the other. So there's kind of a correlation that is well known between H naught and S8 when you consider beyond lambda CDM models, and that often causes difficulty in solving both of them together. So, interacting dark sectors, as we found out through our investigations, is that it kind of helps ease the clustering tension without worsening the Hubble tension. Not to the extent that I can be super proud of, but still, there are certain trends that are interesting, and that is what I'm going to discuss. So, let me clarify before proceeding. Our objective was not to solve every problem in cosmology or solving tensions. Our objective was interacting sectors are interesting. People have studied this in the context of tensions. What happens when we subject it to latest data sets? what are the parameter degeneracies? How do things pull and push on each other, and how it will stand the test of time when future data comes in? So that is probably the main motivation behind this line of investigation. So we consider in this, in this line of work, we consider models where dark energy and dark matter. So here we consider models where dark energy and dark matter can exchange energy via non-gravitational coupling between two dark components. That is all. We don't get into microphysics. We just say that there's an energy exchange between these two components. But why consider interactions at all? Of course, as I already mentioned, that they are useful intentions, but also there is no fundamental reason why they won't interact. We do not know enough about dark energy and dark matter to rule it out from fundamental principles. So in these contexts, these models have also been explored. In this context, this is very interesting to look at. Also, initially, interacting models were proposed in the context of the coincidence problem, in the sense that they can explain why dark energy and dark matter have comparable densities today. Of course, how successful interacting models would be for the coincidence problem depends on the strength of the interaction that is permissible by observational data sets, which is also something that I'll be showing. So the goal of our work was to test these interacting scenarios using current cosmological data and to see whether they genuinely help with tensions, as many people have proposed in the past. So how do we actually do this? Well, we start from the standard continuity equations for two fluids and introduce a phenomenological interaction term, which we call Q, which allows energy exchange between the two sectors. Now, there are several forms of this interaction in the literature, but we take a particular form. We take the form as this. It is like proportional to H with the constant proportionality factor Q, and it is proportional to the density of dark energy. Now, I should say that there is no first principles field theoretic derivation of this particular form. We only take this because previous studies have shown that this works better or is observationally more preferable when it comes to tension, especially the Hubble tension. So we chose this form. That is the only motivation that we have for this choice, and then we roll with it. So once we choose this form and we take this sort of formalism, we solve the background equations, the solutions of which you can see on the screen, and at the perturbation level, we do it in the synchronous gauge. We have four coupled equations for the density contrasts and velocity perturbations for both the dark components. The key point is that we include perturbations in both sectors, not just dark matter. So we even keep CS squared, the sound speed of dark energy, as a free parameter to begin with. Now, there's a technical issue I should mention before we get into the MCMC constraints. If you look at the perturbation equations, in one of them, there's a term 1 plus W in the denominator, where W is the dark energy equation of state. So at W equal to -1, these diverge. Now, for non-interacting models, what people usually use is the parameterized post-Friedman formalism, which handles this automatically. It considers sort of an extra parameter which is not discontinuous at the crossing and stuff like that, and this is what class uses by default. So there is no issue when you're working with non-interacting models. For interacting models, the PPA formalism does not work because it assumes that your dark energy component does not exchange energy with anything else other than through gravity. So we did not develop a separate PPA formalism for interacting scenarios. What we did instead was we did the analysis in the two different regimes. In phantom, where we consider W to be strictly less than -1, and in non-phantom, where we consider it to be greater than -1. This is just to avoid any numerical stabilities when we are finding parameter constraints. That's it. Okay. So moving on. So we incorporate these equations into some Boltzmann solver. We use class here, and we have to use sort of some Romberg integration kind of things to solve the background equations, because it has sort of double integrals which we need to solve to get the background density parameters. And then once we modify class, we obtain constraints using Monty Python, using CMB measurements from Planck 2018, supernovae from Pantheon Plus, yes, from Pantheon Plus, and BOW data from SDS's data release 16. So this was work which was done before DESI came out. I will come to DESI, but initially these results are with SDS's DR16. So now interacting dark energy has been studied quite a bit in the literature. I mean, similar studies have been done by other authors, but our analysis differs in a few important ways. So first of all, we allow dark energy to be dynamical. So many earlier works fixed it to a to be a cosmological constant or assumed a constant equation of state. Instead, we explore multiple parameterizations. So we take interacting lambda CDM as the baseline. Then we can also consider interacting WCDM with a constant but free equation of state, something which many other authors have done. But we also we consider three other dynamical parameterizations such as CPL, the Chevalier-Pulaski-Linder parameterization, JBP, and something called MEDE. So it's modified emergent dark energy. It's just another form that we considered for this study. The reason we do this is we want to look for general trends which are kind of robust across these different parameterizations, if any exists. So that is why we want to take multiple form. So I guess I don't need to get into the discussion. Okay, I'll skip the discussions of what CPL, JBP, and MEDE are. What you need to know is these are different functional forms of the functional parameterizations of the dark energy equation of state. Now, once we have chosen that, the other point which I was mentioning is kind of different from what people usually do, is that members in the audience here would know this better than me, is that certain combinations of the value of the equation of state and the value of Q, or rather the signs of these quantities, can lead to early time instabilities in the perturbation equations. And hence, what the community usually does is they put hard bounds on the parameter Q. For example, if I recall correctly, I might mess this up, but if you're in the phantom regime, that Q should be positive, otherwise there'll be instabilities and so on. There's a certain set of rules which you have to follow. And this is done so that your NCMC analysis or your equations don't run into numerical errors. What we did was we did not put any hard bounds on Q, although we should, and we just said, okay, let the data decide whatever Q and W it wants to choose, and without surprise, the chains converged towards values which are, I mean, stable, which are expected to be stable theoretically. So of course you can always put hard bounds and do it, but in the spirit of data-driven cosmology, we kept a wide prior on Q. So that's just the other thing that was different in our analysis compared to what others had done at that point. Fine, so that's about methodology and what model we are considering. So what do we ultimately find? So coming to the results. Now, I don't expect you to see this. Okay, I can zoom into this. So perfect. So let me first start with the non-phantom regime. So here we see that for any for any interacting model beyond lambda CDF, like for WCDM, MEDE, CPL, or JBP, you'll notice that sigma takes unrealistically large values, and in some cases it goes beyond 1. And this corresponds to gross overproduction of structure that is simply not observed. You don't expect this to happen. So the physical reason why this is happening is that in the non-phantom regime, there's a negative correlation between W naught and Q. I'll show you the contour plots in a moment. You just need to believe me for now that there's a negative correlation between W naught and Q, and this causes the chains to prefer a negative Q values because W naught is greater than -1. Which means energy flows from dark matter into dark energy in our sign convention. As a result of this, dark matter gets depleted, so omega m gets reduced, and there's also a sort of a negative degen. Am I saying this? Just a minute. So omega m increases, and. Yeah, so omega m is suppressed, and there's a negative correlation between omega m and sigma 8. So that increases sigma 8. This happens due to the degeneracy structure. There's another way to see this. It is that at the perturbation level, the interaction terms which get introduced, the extra terms that get introduced, they modify the effective evolution of the dark matter fluctuations. So, in particular, for negative values of Q, the effective friction term in the dark matter velocity perturbation equation is reduced. Let me go back to the equation. I think that will make it easy to see. Um, yeah, it's this one. Yeah. So here, when Q is negative, then the friction term gets reduced. So this leads to larger values of sigma because fluctuations grow faster. So as a result of this, in the non-phantom interacting models, these are not very viable for addressing the clustering tension because it pushes sigma 8 in the opposite direction to what we actually wanted to go in. And that is why they provide no benefit over standard dynamical dark energy and non-interacting dynamical dark energy models on the Hubble tension either. So, so the more interesting scenario is actually the phantom regime. In the phantom regime, it tells a very different story. Here, W is less than -1 throughout. So the dark energy density grows with time. And there's an energy injection from dark energy to dark matter, just the opposite of what happens in non-phantom. And due to this, dark matter is continuously sourced and it dilutes more slowly than 1 by AQ. As a result, omega m is pushed to higher values than in non-interacting lambda CDM. And again, due to the same degeneracy between omega m and sigma 8, higher omega m is accompanied by a lower sigma 8. So to sum up, what is happening is due to these different correlations, when the equation of state is less than -1, Q prefers positive values. As a result of that, omega m decreases. No, sorry. Yes, omega m decreases, and due to that, sigma 8, sorry, omega m increases and sigma 8 decreases. So in the phantom regime, there's some sort of a relaxation of the clustering tension. What happens to the Hubble constant? It does not change. So the moment you introduce this extra parameter Q, this correlation between sigma 8 and H naught almost vanishes, and H naught does not have a correlation with Q either. So H naught is not shifted. It doesn't get better. It is not worsened either. But the sigma 8 value goes higher as Planck wants it to be. So that is probably the main finding that we found, that given this sort of interaction term, if you take a dynamical equation of state of dark energy and you restrict it to the phantom regime, the clustering tension will be eased without worsening the Hubble tension. Yeah. Okay. So these are the detailed contour plots that I was from which I was drawing these conclusions. I will leave them here for just a few moments for you to have a look, and if you have any comments thus far, else I'll move on. If you have Q very large, there is a chance of dark matter or a fraction of dark matter getting warm, for example, because there's an energy injection from dark energy to dark matter. We were worried about this. So what we did was we redid the analysis and kept the equation of state of dark matter as free parameter, just to see if it deviates from zero. So that will tell you whether this Q is really very large or not. We found that it is actually very, very close to zero. So whatever energy exchange is happening, it's not a lot in that sense. Mm-hmm. So that's what I'm showing on the right side plot. So this red one that you can see, this is very strongly constrained to WDM equal to 0. So that's one of the tests we did. The other test that we did was we wanted to see, when we did this analysis, we fixed the sound speed of dark energy, the CS square, to 1. And we do this mainly to speed up analysis, and because there's not really any strong constraint that we have on CS square. But we wanted to see, well, in the future, if you have some constraint on CS square, will our conclusions change? So we did one case. I think that we did this for the interacting W uh, CDM model, I guess. I'm not very sure if this is CPL. This is WCDM. Now, for this case, we kept CS square open and we gave it a wide pry. I think we gave it around minus 1 to plus 1, something like that. We saw that there are no constraints on this parameter. I mean, the data sets that we considered, Planck, Bow, and supernovae, they cannot constrain CS square. Uh, in addition to that, the other constraints don't change. So that means this tells us two things. The first thing is, of course, that current data cannot constrain CS square. The other thing is, even if CS square is constrained from some future mission or some large scale mission in the future, these conclusions would not change because the other parameters are not really sensitive to what the actual value of CS square is. So these are two sort of consistency tests we wanted to do, or extension tests, if you may, to whatever analysis we did. There's a third thing we wanted to explore, and this has to do with redshift space distortion data. So measurements of F sigma 8. So when we included redshift space distortion data or RST data, they kind of tighten the parameter space. As you can see from the contour plots, RSP helps tighten the constraints on many of the parameters. And in fact, constraints on omega macro and sigma 8 and Q increase quite a bit, as can be visually seen. However, the S8 or the sigma 8 numbers that we got when we included RSD, they jump up a bit. I mean, which means that even in the phantom regime and everything that we have done so far, the tension alleviation is somewhat reduced when you include RSD data. Now, why does this happen? Partly because because you are including growth of structure data. Initially, we only had background data. I mean, we have CMB, but late time growth of structure data is being introduced. So that might play certain part in this happening. But there's also a systematic concern. So these F sigma 8 measurements, or at least the compilation that we considered, these are extracted from surveys using some sort of a fiduciary model, which is often lambda CDM. So we are suspecting that maybe this is happening because you're using data which is built on a fiduciary model that is lambda CDM, but you're constraining IDE models. So maybe that's the reason why this tension elevation is decreasing. So what needs to be done is we need to reanalyze this data, this RST data, by assuming the interacting model as the fiducial and then doing this analysis. So that is something that we want to do in the future, but we just wanted to see what would happen with RST datasets. Yeah. Okay. So I guess now I'll move on to the part that I guess excites a lot of people. I'm not sure about audience member here, but DESI. So this forms the part of a second paper in this series of works, where what we did was we just simply replaced SDS's DR16 bow data with DESI DR2. That's all we did. The main finding is that precision improves, of course, because DESI gives you more precise data for bow. That is the first thing. We also noticed that again, this table is very small to see, but I'll just zoom in if this is possible. Yeah, you can see that in the phantom, these are all for the phantom regime. We did not do it for the non-phantom regime because, again, it's not very interesting from a tension point of view. So we see that when Q is greater than 0 in the phantom regime, omega matter takes values which is very high. It's around 0.38 and 0.39. And this is about 4 sigma higher than the non-interacting CPL value. So this is a consequence of the positive Q, which is sourcing dark matter, as I already mentioned. Whether this high omega matter is consistent with data sets like cluster counts and weak lensing observations is something we need to check, which we haven't done that explicitly yet. But this is something that needs to be kept in mind, and again, something that we want to do properly before claiming that these models are very good in the context of tensions, especially given that DESI has such high precision. So that's a small caveat that we found. Also, when we did this DESI analysis, we did some model comparison tests. So I think we computed the Bayesian evidence of these models, and we found that interacting models are not really favored much to their, non-interacting counterparts. And this was a bit worrying. So we wanted to understand why, we saw that the chi-square values, they don't change a lot when you introduce interaction. I mean, let's say you're considering non-interacting CPL and interacting CPL. You're introducing an extra parameter Q, but the fit does not really change much. But Bayesian evidence or AIC, BIC, things like these, they heavily penalize extra parameters. So in that sense, those metrics say that interacting models are not do not improve the fit and are not favored. However, that being said, the motivation for exploring these models is sort of physical in the sense that they help with tensions and maybe hopefully with the coincidence problem and other issues. And it is not really, we are not really saying that, oh, see, interacting models fit the data better yet. At least with current data, we don't see that. So this is another thing that we found out when we did this DESI analysis. Now, of course, any discussion with DESI is incomplete if I don't talk about the evolution of dark energy. So, of course, we wanted to see how the equation of state, the W of Z, varies when we open up interaction. So, in the non-interacting CPL case, the W naught is around minus 0.8 and WA is around minus 0.6. So this corresponds to around W negative 1.4 at very high redshifts, which means dark energy was strongly phantom-like in the early universe, which we all know from the DESI paper. In our interacting CPL phantom case, W naught is constrained to greater than minus 1. I mean, it's phantom, but it's greater than minus 1. We couldn't get a full constraint on it. And WA is somewhat less in the sense it's negative 0.33. So the early universe equation of state when you open up interaction is about negative 1.35. It is still phantom, but it is a bit less extreme. So if you see the evolution of the equation of state, okay, I don't have the plots for DESI here, but I'm sure many of you know that the DESI plot goes something like this. It's quintessence here, and then it crosses somewhere here, and it goes heavily into the phantom regime. We saw that when you open up Q, this evolution, of course, that caveat remains that we are limited strongly to the phantom regime. But what I want to say is this evolution is somewhat smoothed out when you open Q. So in a sense what is happening is this interaction is absorbing some of what WA needs to do in the non-interacting case to fit the DESI data. So a non-zero Q sort of compensates for this large WA deviation. Of course, we can only make a stronger comment when we are able to incorporate this full phantom crossing in the analysis. Also, the chi-square values are comparable to, as I said, I already said the chi-square values are comparable, which means that DESI claims dynamical dark energy with some sort of confidence on the fit, right? Since when we are opening up Q and this WA is decreasing, I mean, WA reduces the dynamical nature of dark energy for the same fit parameter, maybe dark energy is not really evolving that strongly, and it's actually an effect of interactions. Who knows? So that is an interesting thing to look out for. But of course, we will only be able to say more when data has more precision and when we include growth of structure measurements into this whole analysis, which actually brings me to our third paper in this series. But before I get into the third paper or the third project that we did on this, I should mention that. Okay, I think I'm missing something. Just a second. Yeah, I mentioned this. Let's see. Okay. Yeah, no, I think we can. I already mentioned that. Okay. So so for our third project. Okay. So now I'll get into the third project and the last part of my presentation. And it is this. Okay. So our third paper or our third project asks this. Given what current data tells us, what will the next generation of surveys say about interacting dark sectors? So for this analysis, we focused on the phantom regime because, again, the non-phantom is something that we don't consider to be interesting. And we focused on the square kilometer array in the post-reionization era and the Euclid mission. We wanted to see what would happen or what we expect to happen when data from these missions come live. So before I describe the methodology for this work, let me spend a couple of minutes on the physical context. Although I'm sure all of you know what reionization is and what 21 centimeter is, I'll very quickly go through that. What post-reionization means and etc. So in the early universe, just after recombination, the intergalactic medium was mostly neutral hydrogen. And starting around redshift of 6, 7, 8, 9, 10, around this redshift, the first stars and galaxies started forming, and their radiation ionized the surrounding hydrogen. Now, this epoch is called reionization. By around Z6 or 6.5, the intergalactic medium was essentially fully ionized, which marked the end of reionization. Of course, this number depends on your model of reionization and many other things, but it's around 5 or 6. After ionization, which is the epoch that I'll be interested in for this project, the bulk of the intergalactic medium is ionized plasma. It doesn't have any neutral hydrogen. But there remains neutral hydrogen inside dense gas clouds within galaxies. And these are shielded from the ionizing radiation all around. These clouds of neutral hydrogen, they can act as traces of the underlying large scale structure in the post-reionization universe. So this is around from redshifts 0.1 to Z redshift of 5, something around that there. So neutral hydrogen has a hyperfine transition, a spin flip transition between parallel and anti-parallel spin states. So it emits radiation roughly in the rest frame frequency of 1420 megahertz, which corresponds to about 21 centimeter, hence the name. It is a very well-known atomic transition at this precise frequency. So when you observe it with radio telescopes, for example, the SK, and you see a different frequency, you can immediately tell at what redshift it is coming from. So you kind of have a tool to map out the universe in 3D along the line of sight and also across the sky. So 21 centimeter observations give you a three-dimensional map of neutral hydrogen across cosmic time. Why is this important? This is important because the observed spectrum, be it intensity mapping or galaxy clustering or even weak lensing with SK, this is sensitive to several cosmological quantities simultaneously. For example, it is sensitive to the Hubble parameter through the line of sight distance, and it is also sensitive to the growth rate through sigma 8, through redshift space distortion, etc., and other growth observables. So this combination of observations from such surveys makes it a powerful multi-purpose cosmological probe. It can simultaneously constrain the expansion history and the growth of structure. And this is where interacting models seem very interesting because they modify both the background and the perturbation sector. So these observations can help put strong constraints on such interacting models. And this is what we wanted to forecast on. So our forecast methodology goes as follows. So first, we need mock data because we don't have the actual data. But the way we generate this mock data is by assuming a fiducial model which is identical to the model that we are going to constrain. So usually when people do forecasts, they generate mock data with lambda CDM and then constrain some other models with that. This sort of, creates a lambda CDM bias in the analysis. But here we did it on a case-by-case basis. So first we take interacting CPL in the phantom regime. We take constraints that we found with DESI in the previous work, and we generate mock data. And then mock data for, so the mock data that we generated for Euclid, and we generated for SK mid, which will probe the post-reionization era. And we did it for a few different configurations. So for example, once you take only galaxy clustering measurements, second you combine it with cosmic shear measurements, or you can just do intensity mapping. So there's a lovely paper by Sprenger et al. 2019, where they have described these different pipelines, and they have also incorporated this into the Monty Python package as a default thing available when you download it. So once we have a modified class, we can easily generate these mock data sets for these different configurations and get forecasted constraints on them. Of course, when you talk about forecasts, you think about Fisher matrices. But here we did not do Fisher matrix forecasting because since these models models are a bit complicated. We expect the correlations to not always be Gaussian. There can be some sort of non-trivial degeneracy structure, I mean, parameter degeneracy structure, etc. To avoid those complications, we did MCMC forecasts by assuming that the mock data is actual real data. And we when we run these MCMC forecasts, we combine these mock data sets with current data sets, because that is what we expect should be done, because you have current data sets and then on top of that you have this new data set. Then what happens? What is the projected error? So that's the methodology. The main thing, the main choice that we have to make while doing these forecasts is at what value of wave number, or at what value of k you consider your observations to be true, because these observations are mostly power spectrum observations, right? And if you don't have a very good handle on what happens in the nonlinear regime, or if you don't know, if you don't have a good theoretical understanding on modeling of the nonlinear regime, you cannot really get constraints on your cosmological model. So we considered two prescriptions for this. The first prescription, which we call the conservative case, is where we limit Kmax to be around 0.2 H per megaparsec. So this is in the quasi-linear regime where our linear theory is somewhat reliable. And this is theoretically safe, but it discards a lot of observational information, because these future surveys, they're expected to probe deep into the nonlinear regime. So if you limit it to 0.2, you're kind of throwing away all that data. So we take another case, which we call the realistic case. And in the realistic case, we extend Kmax to almost 10. I mean, for galaxy clustering, 10 H per megaparsec. And for cosmic shear, we extend it to around 2 to 5. As you can well understand, if you go deeper into the nonlinear regime, you'll get better constraints, subject to the condition that you understand your nonlinear modeling very well. But these are the choices that we made to get these forecasts. So once we do this, we get the forecast. The results that we get is, for example, the one that I'm showing you here on the left. This compares how SK intensity mapping would forecast parameters in the conservative and realistic cases. So if you see the plots here, you'll notice that the realistic cases have slightly tighter error bars than the conservative cases, which you would expect because you're probing into the deep nonlinear regime. The other results that I have, because we considered many different combinations of these configurations. So this is a big table. Again, I don't expect you to have a look at these numbers, but these are the combinations that we took. We took SK1 band 1, we took SK1 band 2, we also compared SK1 and SK2, and so on and so forth. And on the right, this is a more visual representation of what happens, and these are the error bars, how we expect them to improve compared to current constraints. This is on a log scale, so you can understand that these constraints are expected to improve by quite an amount. I mean, we expect that. I don't know if this is too optimistic, because we are choosing very high values of Kmax. But of course, if we have a good handle on a nonlinear theoretical modeling, we can hope to get constraints like this. So these plots, I think, again, you can't see this, but I tell you, this is for S8, this is for omega M, this is H0, W0, WA, and Q. So all the parameters that are most important or most interesting, they all are promised to be constrained to a high precision. I think I'm running out of time. In that sense, I will not go into the details of every combination that we compared. The general trend that you can see from here is that compared to current observations, whatever mock configuration you take, you expect precision improvements by factors of 10, 15, 20, or in some cases even 40. Of course, we are a bit suspicious why you would expect precision improvement by 40. Maybe we are making some simplistic assumptions when we are generating mock data sets. But the main thing remains that these future surveys will kind of be definitive in helping constrain interactive models and telling us whether we genuinely have signatures of a non-zero Q, and if they can help with tensions and dynamical dark energy and so on. So I'll not get into the details of this. Just like in the spirit of our previous projects, we wanted to do some consistency checks. So these main results that I showed, these are for these are for interacting CPL in the phantom regime. We wanted to see if the true description of the universe is non-phantom. If it is non-phantom, then whether SK and Euclid can place any constraints on these parameters. We see that they can. So in that sense, it's not that SK would fail to provide constraints if your equation of state is in the quintessence regime. It will be able to provide competitive constraints. Also, we tested the CS squared test again. We kept CS squared open and wanted to see if these mock data sets can put any constraints on those. Of course, they can't, because to get constraints on CS squared, you would need large scale structured data, but these probe mostly small scale structured data. So we don't get any constraints on that. Also, why limit to CPL? We also wanted to see what happens with JBP, and again we see the same improvements in the constraints. That is, so we are saying that okay, this methodology or SK and Euclid will be able to place constraints no matter what is the equation of state of dark energy that you assume, or I mean, whatever equation of state of dark energy is the actual model of the universe, and I mean, it will be independent of CS square and etc. So this work has less to do with tensions, but more to do with that with the fact that if you take interacting models, whether future surveys can place strong constraints on it. What are a few open questions? Yes. Yeah. So, what happens after we did all this? The first and most pressing issue is, of course, the phantom crossing. We did not model the interaction where W crosses -1. This needs to be done. Otherwise, we cannot like compare it directly to what Desi predicts for the equation of state and so on. So this comparison requires a proper PPF formalism, or it requires one to develop some sort of a what do I say, a microphysics model for this sort of interaction. Only then we can maybe consider crossing in these interacting scenarios. So this is kind of non-trivial and ongoing, and I would appreciate if any of you have any ideas in this direction. We are trying a few different things, but yeah, not something that we have been able to make much progress on yet. The second thing is, of course, regardless of that phantom thing, what is the microphysics that is happening? If you are convinced with the results that I just presented, then you would be then you are basically getting convinced of the fact that an interaction which is proportional to rho dark energy is interesting, or it might be the next big thing after lambda CDM. But where does it come from? This is a purely phenomenological form. So that is something that one can think about. That is there any some sort of a fundamental physics description that can effectively give this sort of a interaction term. The third thing is, of course, as I mentioned with my RSD example, many of the data sets that we considered, they have sort of a lambda CDM bias in it, because these data sets are extracted using a lambda CDM template. This is very well known for BAO. Of course, for BAO, if you don't deviate much from the fiducial model, there's not really any issue. But some studies have shown that if you extract BAO assuming a fiducial lambda CDM and then constrain something very different, there can be biases. That is something that worries us. That might be playing some role in this analysis. Also, RSD is extracted assuming lambda CDM as the fiducial. So these data sets need to be reanalyzed assuming interacting models and then constraining them to see whether they really have these tension resolving properties that I'm showing you or not. So developing interaction consistent likelihoods is important future work. The fourth thing is nonlinear structure formation. Of course, future surveys will give you information to very high K values, but if you don't understand what is happening at the small scales, baryonic feedback and other stuff that I'm really not an expert on, if you don't have a good handle on those, you cannot really extract meaningful cosmological information with all that small scale structure formation data that you will get from these surveys. So that is something that we need to work on and develop on. And we did not consider those complications in this work. For example, in the realistic scenarios that we considered, we just said, oh, okay, Kmax is 5 or 10. We didn't really say, okay, why is it 5 or 10? Or how can you be confident that 10 is reasonable? Uh, I mean, it can be a realistic assumption and so on and so forth. That is something that needs to be taken into account into these analysis. The fifth thing is in the introduction term that we took, this Q proportionality factor that we have, it's taken to be a constant. But many studies have shown that this Q may evolve with redshift, it may be scale dependent, etc. If that happens, then there will be nonlinear effects on the matter power spectrum. So these are also something, I mean, these are extensions of this study that could be interesting in this context, especially since high precision data sets are coming up. And finally, as I think I've already mentioned a couple of times, interacting models are not really favored when you subject it to model comparison metrics. So at the moment, the motivation for these lies mostly uh, theoretical and observationally from a tension perspective. They don't really improve the fit to the data, but they don't worsen it either. So that is also something that we need to keep in mind when you're talking about these models. So to summarize, interacting dark energy dark matter models remain a viable and interesting extension to lambda CDM in the context of current data. In the phantom regime, of course, they can help reduce the clustering tension without worsening the Hubble tension. But of course, as precision data, particularly from DESI, DR3, DR4, DR5, and upcoming observations from SK, Euclid, Rubin, etc., come, they will tighten the constraints and limit the available parameter space more. Of course, this leaves us with an exciting possibility, as I think Amit was mentioning, that would future data show hints of non-zero Q in the dark sector, or would lambda CDM be the model of the universe? So that is what makes the next decade or two really exciting for this kind of work. And also, I mean, as for now, I feel that these tensions that we have in cosmology, and this has mostly been the main theme of my PhD, is that they'll make us look bad in the sense that we don't understand the universe well. Cosmologists are not doing their job very well, but they also keep our lives very interesting. And not to mention, this is what keeps open the prospect of discovery and new physics that would possibly be the reason behind these tensions. So I should clarify once more what I'm claiming in this talk. We claim that a physically motivated framework that is consistent with all current data produces interesting parameter correlations, and it will be tightly constrained by forthcoming observations. What we do not claim is a confirmed detection of Q or a formally preferred model over lambda CDM. Such a strong statement would only require more work